Lecture 24 of Vector Calculus. We're getting to the end. Final exam is in about a week and a half. It's Monday, May 20th in Gillette Hall, room 203. And the exam starts at 11:30 and ends at 1:30. In the middle of what we're covering in chapter 17. So in chapter 17, we're studying sections 1 to 4, and this is on the subject of vector fields. And a vector field is a function that sends a vector to a vector. So a vector field in R2 is simply a function f from R2 to R2. So for any vector xy in R2, f of xy is another vector in R2. So it has two components. The first I write as lowercase f of xy, and the second is lowercase g of xy. So that's a vector field in R2, and there also are vector fields in R3, but just to keep things simple, because we don't have a lot of time, I'm going to concentrate on vector fields in R2. And one example or one method to get a vector field is if you have a scalar field. So let phi be a function from R2 to R. For example, phi of xy might be x cosine y. And the gradient of phi of xy is a vector. It's the partial of phi with respect to x and partial of phi with respect to y. So for any xy, this is in R2. So for example, if this is my function phi, the partial of phi with respect to x is cosine y. Partial of phi with respect to y is minus x sine y. So the gradient of phi at any point xy is equal to cosine y minus x sine y. And f equal gradient of phi is a vector field. It's for every vector x, you get another vector. For every vector xy, you get another vector. So not every vector is of this form, but we say the vector field f is conservative if the vector field f is the gradient of some scalar field phi for some function phi. And phi is called a potential function. For f. So one very nice kind of vector field is a conservative vector field. And I want to explain two things. First, why they're so nice, and assuming they are nice, how do you determine if a vector field is conservative? So here is a necessary condition for a vector field F to be conservative. So suppose F of xy is, these are the coordinate functions, little f and little g of xy. If f is conservative, that means if f is the gradient of phi, then, let's see, f at xy is the partial of phi with respect to x, that's the first coordinate, and the partial of phi with respect to y, that's the second coordinate. So my function f, little f of xy, is the partial of phi with respect to x, and g is the partial of phi with respect to y. So if the vector field F is conservative, then there's a scalar field phi such that the first coordinate of F is the partial of phi with respect to x, and the second coordinate is the partial of phi with respect to y. But then what happens? If you take the partial of F with respect to y, that's the partial with respect to y of the partial of phi with respect to x. So that's the second partial derivative of phi with respect to x and y. And the partial of g with respect to x, you take the partial with respect to x of the partial of phi with respect to y. And if phi is continuous partial derivatives and everything is nice, the order of differentiation doesn't matter. If you differentiate phi first with respect to x and then with respect to y, you get exactly the same thing as if you differentiated first with respect to y and then with respect to x. So that means the partial of f with respect to y equals the partial of g with respect to x. So this is a necessary condition for a vector field to be conservative. See, let's look at our example. We had an example a moment ago where we had a conservative vector field F equal to cosine y minus x sine y. So in this vector field, this is my function little f of xy, and this is my function g of xy. It is f of xy equals cosine y. G of xy is minus x sine y. If I take the partial of f with respect to y, I get minus the sine of y. If I take the partial of g with respect to x, I get minus the sine of y. So in this example, partial of f with respect to y equals the partial of g with respect to x. So this is just an instance of this phenomenon. So the conservative vector field is the gradient of a scalar field. And if a vector field is conservative, then if you take its first coordinate and differentiate with respect to y, you get exactly what you get when you take the second coordinate and you differentiate with respect to g. And in fact, if the partial derivatives of f and g are continuous, if it's a nice function, then in fact the opposite, the converse is true. So this is the theorem, which says the vector field f the coordinate function f and g is conservative if and only if the partial of f with respect to y equals the partial of g with respect to x. So this is the notation the book uses, but of course, f sub y means partial of f with respect to y, g sub x means partial of g with respect to x. So this is the same. So this is a test for a vector field to be conservative. Let's look at an example. And pick some homework problems. This is in section 17.3. If we look at problem number 17, suppose we have the vector field f equal to xy. So the first coordinate x is my function little f of xy, and my second coordinate y is my function g of xy. If I take the partial of f with respect to y, I get 0. I take the partial of g with respect to x, partial of y with respect to x is 0, so they're equal. So this is conservative. That means there exists a function phi such that the gradient of phi is equal to f. So we have the following problem: find the potential function phi. Find phi. So phi has the property that the partial of phi with respect to x, the partial derivative of phi with respect to x, is equal to x. So what is a function phi whose derivative is x? So phi is the integral of x dx. So this means the integral of x is a half x squared. And we would normally say this is plus a constant, but what we have to understand is the partial of phi with respect to x is x. So this is something whose partial derivative with respect to x is 0. So this could be any function of y. So phi is a half x squared plus some function of y. And for this function phi, the partial of phi with respect to y is y. So that means phi but this is phi. So the partial, so if this is phi, what is the partial of phi with respect to y? Partial of phi with respect to y is the partial derivative with respect to y of a half x squared plus h of y. This doesn't involve y. This is a constant with respect to y. The partial derivative of this with respect to y is 0. So this is just the derivative of y. And that's equal to y. So what is a function whose derivative is y? H of y is a half y squared plus any constant. So phi of x and y is a half x squared plus a half y squared plus a constant, and I can just as well take the constant to be equal to 0. So this analysis shows that starting with the vector field f equal to xy, it's conservative, and I found a potential function. Let's just check. What is the gradient of phi? So the first coordinate is the partial of this with respect to x, which is x. The second coordinate is the partial derivative of this with respect to y, which is y. So that's equal to f. So, so there's a lot going on here, and it really takes an investment of time to understand it all. But let's look at number 19 in the set. We have the vector field f of x, y equal to x cubed minus xy, x squared over 2 plus y. And the problem is determine if it's conservative, and if it is conservative, find the potential function. So this is my function f, and this is my function g. What is the partial derivative of f with respect to y? It's minus x. What is the partial derivative of g with respect to x? It's plus x. Differentiate this with respect to x, you get x plus g. Partial of f with respect to y is minus x. Partial of g with respect to x is x. They're not equal. So therefore, f is not conservative. Let's look at another example. Suppose you have problem 21. We have the vector field xy, the vector, divided by square root of x squared plus y squared. Well, let me just write this. The first coordinate, this is a scalar, this is x over the square root of x squared plus y squared. And the second coordinate is y, the square root of x squared plus y squared. So for this vector field, the first coordinate, little f of x, y, is x over square root of x squared plus y squared. And the second coordinate is y over the square root of x squared plus y squared. Let's see. If this is f, what is the partial of f with respect to x? So by the quotient rule, it's the denominator squared, which is x squared plus y squared. It's the derivative of the numerator, which is 1 times the denominator, minus the numerator times the derivative of the denominator. The derivative of the square root of x squared plus y squared is 1/2 x squared plus y squared to the minus 1/2, 1 over square root of x squared plus y squared, times the derivative of x squared plus y squared with respect to x, which is 2x. So this looks like square root of x squared plus y squared. The 2's cancel, minus x squared over the square root of x squared plus y squared. For x squared plus y squared. That's correct, but I made a mistake. I should have differentiated f with respect to y. Let me just have a big piece of paper. So start this again. This is number 21. I have the vector field F, which is the vector xy divided by its length, which is x over the square root of x squared plus y squared, y over the square root of x squared plus y squared. So this is little f of xy, this is g of xy. The partial of f with respect to y is, by the quotient rule, if you like, square the denominator. The derivative of the numerator with respect to y is 0, minus the numerator times the derivative of the denominator, which is 1 over 2 square root of x squared plus y squared, differentiating with respect to y, times 2y. So this is minus, the 2's cancel, xy over x squared plus y squared times the square root of x squared plus y squared, the 3/2. This is g. What is the partial of g with respect to x? It's over the denominator squared. The derivative of y with respect to x is 0, minus y times the derivative of square root of x squared plus y squared with respect to 0, which is 1 over 2 square root of x squared plus y squared. Derivative with respect to x is 2x. And again, the x's cancel. This is minus xy over x squared plus y squared to the 3/2. If you compare these two, they're equal. Partial of f with respect to y equals partial of g with respect to x, which means f is a conservative vector field, which means f is the gradient of phi for some potential function phi. And what do we know about phi? The partial of phi with respect to x is the first coordinate, x over the square root of x squared plus y squared. Which means if I integrate phi of xy is the integral of x over the square root of x squared plus y squared dx. So I have to find the antiderivative of this. And now, unfortunately, we use the fact that you've taken calculus and you're supposed to remember. See, this is the integral of x squared plus y squared to the minus 1/2 x dx. In this integral, if I make the substitution, u equals x squared plus y squared, du dx is 2x. So du is 2x dx. I have x dx. I can make this a 2 if I multiply by 2 and divide by 2. So if I make this substitution, this becomes the integral of 1/2 u to the minus 1/2 du. And the integral of u to the minus 1/2 is 2 u to the plus 1/2. Plus something which is constant with respect to y. The 2's cancel. This is square root of x squared plus y squared plus h of y. So phi of xy is the square root of x squared plus y squared plus some function of y. If I differentiate phi with respect to y, again, by now you should know how to differentiate all this. You get y over the square root of x squared plus y squared plus h prime of y. And the partial of phi with respect to y is equal to y over the square root of x squared plus y squared. So h prime of y is 0. So h is just a constant with respect to y. So I get that phi of xy is the square root of x squared plus y squared. Let's check. What is the gradient of phi? If I differentiate phi with respect to x, I get, this is x squared plus y squared to the 1/2. I get 1/2 x squared plus y squared to the minus a half times 2x. That's x over the square root of x squared plus y squared. If I differentiate phi with respect to y, I'll get y over the square root of x squared plus y squared. So the gradient of phi is x over the square root of x squared plus y squared, comma y over the square root of x squared plus y squared, which is the same as the vector xy divided by its length. And that's equal to f. So we found that the function, the vector field f is conservative, and we computed a potential function for it. Let me pause for a moment so you have a chance to look at this, and if you have a question, this is really good time to ask a question. Now, just as there's a fundamental theorem of calculus in Math 175, 176, the functions of one variable, there is a fundamental theorem for line integrals. And it says the following. Suppose we have a conservative vector field f, which means it's the gradient of some function phi, scalar function phi, where phi is differentiable and really nice. And you have a curve C that goes from A to B. So you have a point A in the plane, a point B in the plane, and you have a curve C that goes from A to B. The integral, the line integral, this is the first line integral. I'm going to review the meaning of these line integrals in a moment, but I just want to state the thing. The integral along the curve of this vector field only depends on the beginning and end points of the curve. It's the value of the potential function at phi minus the value of the potential function at A. And what this means is that the value of it for a conservative vector field, the value of the line integral only depends on the starting point and the end point of your curve. You have another curve from A to B. Any curve from A to B. The integrals along all of these curves are just phi of B minus phi of A. It doesn't depend on the endpoint. So the line integral is what we call path independent. If you take any path whatsoever from A to B, the line integral along that curve, along that path, has the same value regardless of the path that you choose. Now, the line integral from A to B is the negative of the line integral from B to A, which says if you, suppose you have a curve that starts at A and ends at A. take some point on that curve. So, and think of two curves. The curve that starts at A and plot out point B. You have a curve from A to B, and then you have a curve from B to A. Now the curve from B to A is the negative of the curve from A to B. So this and this are equal, but this is minus this, which says if you have path independence, the integral along a closed curve from a point to itself, and we usually denote a closed curve because it looks like a circle, with the integral sign with the 0 around it. That's the value 0. Just going halfway around and then back, those two cancel each other out. So for a C is a closed curve. That means it starts and ends at the same point. The line integral of a conservative vector field around a closed curve is 0. So I'm going to come back to this in a few minutes, but I want to just review line integrals. A line means a curve. So a curve is given by some function r of t. T goes from A to B. And the components of r of t, if it's a curve in the plane, you have an x component and a y component with the functions of t. So you start at r of little a, you move along the curve, r of t, and the endpoint is r of little b. Sometimes we write capital A for the starting point and capital B for the end. But that's a curve. And we have a scalar function f of xy. So at every point in the plane or in whatever region of the plane the curve is sitting in and where the function f is defined, for every point xy, we have a number f of xy. Right? A number is assigned to every point in the region. It's a scalar. And our sense of this line integral, this is the definition of the line integral, which we write as the integral around the curve C of f of x of t, y of t, ds. If you take some piece of the curve and it has some length, delta s, and at some point in that little piece of the curve, we compute f of xy. We can take f of xy times delta s, and we add that up for every piece of the curve and take smaller and smaller pieces, and that limit, if it exists, is what we call the line integral. So there's a definition which is completely analogous to the Riemann integral in Calc 1 and 2, where you had an interval from A to B, you divide it up into pieces of size delta x. In each piece, you picked a point and you computed f of xy. You take f of xy times delta x and add up those pieces. And that was take the limit, and that was the definition of the integral of your function. One interpretation of which was the area under the curve, but lots of it. So the analogous thing in the plane, when you have a curve replacing the interval and a function defined on the curve, Every point on the curve, you get a number. Just as in Calc 1, on every point of the line, you got a number. This is the line integral. And the way this is calculated is, this is the integral from a to b of f of x of t, y of t, the absolute value of r prime of t, dt. So from the calculational point of view, you have to compute a line integral. This is what you compute. So for example, actually in section 17.2, number 18, we have the function f of xy equal x squared minus 2y squared. And we have the curve r of t, which is given by t over the square root of 2, t over the square root of 2, for t between 0 and 4. Now, if you graph this, this is just part of a straight line along y equals x. When t is 0, you're at 0. When t is 4, you're at the point 2 root 2, 2 root 2. This is r of 4. This is r of 0. So our curve is just a straight line from here to here. And if this is r of t, when you differentiate this, r prime of t, this is just the derivative of t over root 2 is 1 over root 2, 1 over root 2. So the integral of this function x squared minus 2y squared ds along this curve C is equal to the integral. T goes from 0 to 4. X and y are both t over root 2. So this is t over root 2 squared minus 2, y squared is t over root 2 squared. Times r prime of t, an absolute value. This is r prime of t. The absolute value of this vector is 1. This is a unit vector. Times 1 dt. This is the integral from 0 to 4, t over 2, minus t squared over 2, rather, minus 2 times t squared over 2, dt. This is t squared over 2 minus t squared over 2 is minus a fourth, the integral from 0 to 4 of t squared dt. That's minus a fourth, t cubed over 3 from 0 to 4 is 4 cubed over 12 minus, which is minus 16 over 3. If I do my arithmetic correctly. That's a line integral. Now, we also have, and this is fundamental, the line integral of a vector field. Along curve C. So here we have our curve C. R of t goes from A to B. And at every point on this curve, we have a tangent vector. So the unit tangent vector T at T, at the point R of T on the curve, is you take the derivative, the tangent vector at any point is the derivative of R prime of T. And if you divide by its length, you get the unit tangent vector. So this is the unit tangent vector. But also at this point, we have the vector field. So this is R of T. Here we have the vector field evaluated at R of T. And we look at the component of the vector field parallel to the tangent. So what we have here, how do you get the component of the vector field in the direction of a unit vector? It's so at the point R of T, the component of F at R of T in the direction of the curve is in the direction of the unit tangent vector T at T is, so this is the component of F in the direction of T. It's the dot product of F of T with the unit tangent vector. Which is F dot R prime of T over the length of R prime of T. And the line integral of the shorthand, this is F dot T. So the line integral of the vector field F along the curve C is defined to be so you get from the vector field F, you get a scalar function at each point on the curve, which is the component of the vector field in the direction of the curve, parallel to the unit tangent vector. F dot T ds. So this is going to be the integral from A to B F dot R prime of T so this is the integral of a vector field along a curve where at each point you're integrating the component of the vector field in the direction of the curve. So this is the line integral of a vector field along the curve in the direction of the curve. This is sometimes called the circulation. Let's do an example. So this is from section 17.2. number 42, see what happens. So we have the vector field F, which is the rotation field minus y comma x. And the curve C is going to be the semicircle of radius 4. So the curve C is given by the function r of t equals 4 cosine t for sine t. And when t is 0, you're here, and when t is pi, you're here. This is for t between 0 and pi. So this is r of t. R prime of t, when you differentiate, you get minus 4 sine t, 4 cosine t. So the integral along the curve f dot t ds. This is the integral from a to b of f dot the r prime of t dt. See, a is 0 and b is pi. Let's see. What is this? Let me compute this dot product. F dot r prime of t. The vector field is minus y. This is y. This is x. So this is minus 4 sine t. X is 4 cosine t. That's f at the point r of t in the curve. Dot product with r prime of t, which is minus 4t, 4 cosine t. When I compute that dot product, I get 16 sine squared t plus 16 cosine squared t, which is 16 sine squared plus cosine squared. Sine squared plus cosine squared is 1. So this is 16. So I'm just integrating the constant 16 from 0 to pi. So that's 16 pi. I did my calculation correct, I hope I did. That's my answer. Let's look at what happens when we have a conservative vector field. So the fundamental theorem for line integrals, if f is conservative, so if f is the gradient of a scalar function phi, then along any curve, f dot t ds, so the curve starts at A and ends at B, going to be phi of B minus phi of A. So let me just do a couple of examples to see if this is correct. Suppose I take the function, this is in section 17.3, number 31. If I take the function phi of xy equal x times y, the gradient of phi, if I differentiate this with respect to x, I get y. If I differentiate this with respect to y, I get x. So my vector field f, my conservative vector field f is y comma x, and the potential function is xy. Suppose I take the curve r of t, which is cosine t sine t, and t going from 0 to pi. So you need to be able to graph this. This is just semicircle, half of the unit circle, going from 1, 0, which is r of 0, to minus 1, 0, which is r of pi. So that's my curve C. And r prime of t is minus sine t cosine t, which would look very similar to the last problem. So the integral around C of f dot t ds is the integral. T goes from 0 to pi. F of xy. F is what? F is y comma x. So f of t is y is sine t. X is cosine t. R prime of t is minus sine t cosine t. So f dot r prime of t is minus sine squared t plus cosine squared t. Cosine squared minus sine squared is the cosine of 2t. So I'm integrating f dot r prime t dt. This means I'm integrating from 0 to pi of cosine 2t dt. That's 1/2 sine of 2t evaluated from 0 to pi. This is 0 minus 0. This is 0. So this integral is 0. But now if I use the fundamental theorem, the integral of this conservative function along the curve C is going to be simply the potential function phi evaluated at the point B, where you end up, minus phi of the point A. A is where you started. So this is phi of minus 1, 0 minus phi of 1, 0. Phi is the function xy. This is minus 1 times 0 minus 1 times 0. 0 minus 0, that's 0. So it certainly checks. Whether we do the line integral explicitly or we do it by applying the fundamental theorem, of course we get the same result. And this way, it was a lot less work. Now, this makes using the fundamental theorem often a very efficient way to calculate a line. Let's look at number 39. Section 17. The integral along a curve C, 2x comma 2y dot dr, where C is any curve from 0, 1 to 3, 4. So I have some curve in the plane from 0, 1 to 3, 4. And I want to integrate this vector field along the curve. What is my vector field? My vector field F is 2x, 2y. And this is a conservative vector field. If I let phi be x squared plus y squared, the derivative of phi with respect to x is 2x, the derivative of phi with respect to y. The derivative of phi with respect to y is 2y. So this is the gradient of phi. So this is a conservative vector field. And this is the potential function. And so the integral of this conservative field along this curve is just going to be phi of b minus phi of a, difference at the endpoints. That's phi of 3, 4 minus phi of 0, 1. Phi of 3, 4 is 3 squared plus 4 squared. Phi of 0, 1 is 0 squared plus 1 squared. This is 25 minus 1. So we get the answer is 24. Let's look at number 41. Number 41, we have the integral along the curve C of a vector field, which is given as the gradient of the scalar function e to the minus x cosine y. This is just one of our 3 of these notations for the line integral. So this is my vector field, which is obviously conservative because it's given as the gradient of this function. So this is my vector field, and this is my potential phi. So this is a conservative vector field, and C is a curve from 0, 0 to the point log 2, comma 2 pi. So this is my starting point A, and this is my starting point B. This is simply going to be phi of B minus phi of A. Phi of B, this is e to the minus x cosine y. So e to the minus x is log 2 cosine 2 pi minus phi of 0, 0, e to the 0 cosine 0. E to the minus log 2 is a half, cosine of 2 pi is 1. E to the 0 is 1, cosine 0 is 1. A half minus 1 minus a half. So let's go back and look again at the fundamental theorem for line integrals. And I want to sketch the proof. So this is the fundamental theorem for line integrals. So we have phi, a potential function that we can differentiate. And so F is the conservative vector field obtained from this differential potential function. And we have some curve C from A to B. And the fundamental theorem says the integral along C of F dot T ds and the integral of F dot dr. These are just two notations for the same thing. It's just the potential function evaluated at the endpoint minus the potential function evaluated at the starting. That's what we want to do. Proof. So suppose R of t is given by x of t, y of t. The t going from A to B. So A is the starting point. It's the R evaluated at time A. Capital B is the ending point. The R of t evaluated at time B. So consider phi of xy in the curve C. So phi at some point R of t, this is phi of x of t, comma, y of t. And by the chain rule, this is the two-dimensional chain rule, just a simple extension of the chain rule that you learned in first semester calculus. d phi dt is the partial of phi with respect to x, dx dt, plus the partial phi with respect to y, dy dt. Which is exactly the dot product of the vector partial phi partial with respect to x, partial derivative phi with respect to y. Dot product with dx dt, dy dt. This is the gradient of phi, and this is r prime of t. And this is f, the vector field, dot r prime of t. So now the integral along the curve, f dot dr, the line integral, is the integral from A to B of f dot r prime of t dt. But f dot r prime of t is d phi dt. And this is just the Baby fundamental theorem of calculus from first semester, second semester. If you integrate a derivative of a function, you get the function. So this is phi of b minus phi of a. Sorry. Phi of capital B minus phi of capital B. It's phi of r of b minus phi of. That's the whole proof. So the fundamental theorem for line integrals for a conservative vector field is just a straightforward application of the fundamental theorem of calculus from beginning calculus. Now there's a extremely interesting alternative method to calculate line integrals for vector fields that are not necessarily conservative. Let me just review. So again, if F is a conservative vector field, and C is a closed curve. Closed means it starts where it ends. Then the integral around the curve is always zero. For a conservative vector field, the integral around a closed curve is zero. But if F is not conservative, this is not necessarily the case. So how to compute the integral around a closed curve of a vector field when F is not conservative? Because in this case, the integral is probably not going to be zero. And the first answer to that question is Greenstone. So if you have a nice closed curve, it doesn't intersect itself, so it's what's called simple. A vector field F, which is not necessarily conservative, but its coordinate functions can be differentiated. It says the following: the integral around the closed. So here we have, this is C, and it encloses a region R. So R is a region inside the curve. So the integral around C of F dot dr is equal to the double integral, right? We learned about double integrals early on. So F has coordinate functions F and G. It's the double integral over R of the partial of G with respect to X minus the partial of F with respect to Y dx. So this converts a line integral of a vector field to a double integral of a function of two values. So to understand what this means, the best thing is just to calculate stuff. So suppose, so here's an example. We take our closed curve C to be the unit circle. So this is 1 minus 1 minus 1. That's, and R is the region inside the circle. Suppose we take F to be the vector field minus yx. So the first coordinate, f of xy, is minus y, and the second coordinate, g of xy, is equal to x. And what is the integral around this closed curve C of the function f dot dr? So let me compute this using Green's theorem. This is the double integral over R. So I'm integrating over the circle. Partial g with respect to x. Partial g with respect to x, partial g with respect to x is 1. Partial of f with respect to y is minus 1. 1 minus minus 1 is 2. So this is 2 times the integral over R of 1. This is just the integral of 1 over a region. It's just the area. Area of a unit circle is pi. The area of the circle is pi. This is 2 pi. And that's it. Didn't have to do any work. Let's look at some more examples. Go to section 17.4. Number 17. We have the vector field F equal to 2y minus 2x. So the first coordinate is 2y. The second coordinate is minus 2x. And suppose we take R to be the region of the plane bounded by the curve y equals sine x and y equals 0 for x between 0 and pi. That's what the sine function looks like from 0 to pi. And this is my region R. Okay. So Green's theorem says, and then we have a closed curve. Suppose the closed curve is start at 0, go along this curve to pi, and then from pi along the straight line back to 0. I want to show the integral around that closed curve f dot dr is the double integral over the region R of partial g with respect to x minus partial f with respect to y dx. So about 2 means to compute. Let's see. What is the partial of v with respect to x? Minus 2x differentiated with respect to x is minus 2. What is the partial of f with respect to y? Derivative of 2y with respect to y is plus 2. So this minus this is minus 2 minus 2, or 4. So on the right-hand side, the double integral over R of partial g partial x minus partial f partial y dA is minus 4 times the double integral over R of 1 dA, which is minus 4 times the area of R. If you integrate 1 over a region, you just get the area. What is this area? This is just the y equals sine x. The area of R is the integral from 0 to pi sine x dx. That's minus cosine x evaluated from 0 to pi. That's minus 1 minus 1, sorry, or minus 1. That I get. Cosine pi minus cosine 0. So that's 1 minus 1 minus is 2. The area under this curve is 2. So the integral from 0 to pi sine x dx is the integral from minus cosine x from 0 to pi. So this is minus cosine pi minus cosine 0. And that's minus 1 minus 1, which is plus 2. This area is 2, and we get minus 4 times 2. Let me just double check that because I'm going to be safe about this. So we have the vector field f of xy is 2y minus 2x. If you take the partial of g with respect to x, I get minus 2. If the partial of f with respect to y, I get 2. So minus 2 is minus 4. So this integral is minus 4 times the area under the sine function from 0 to pi. And so we integrate sine x from 0 to pi. That's minus cosine x. That's equal to t. So minus 4 times 2 is minus 8. Okay, has to be right. So if I evaluate the right-hand side of Green's theorem, I get minus 8. So I also want to evaluate the left-hand side. So the left-hand side is the integral of this function along this curve. And this curve has 2 pieces. So let me draw it again here. Going from 0 to pi, if y equals sine x is the curve. So I'm going to write my curve as having in 2 separate pieces. So the first is, as I get from here to here, r of t is t sine t from t going from 0 to pi. And t is 0, you're at 0, 0. And t is pi, you're at pi 0. Let's call that r1 of t. And r2 of t is the straight line from pi back to 0. So I can say as t goes from 0 to pi again, I can let r of t be pi minus t. Because when t is 0, this is pi. And as t goes from 0 to pi, pi minus t goes from pi down to 0. So the integral around this closed curve of f dot dr, call this C1 and this C2. This is the integral around C1 of f dot dr plus the integral around C2 of f dot dr. I have to calculate these two separately. So the integral around C1 of f dot dr is the integral t goes from 0 to pi. What is that? And what is my function, my vector field f? My vector field x, f is 2y minus 2x. So at f at r of t, it's going to be, here's my r of t, t sine t. This is 2 sine t minus 2x minus 2t. So this is 2 sine t minus 2t, dot product with r prime of t, r1 prime of t, r sub 1 prime of t. I differentiate this, I get 1 cosine t. Dot product with 1 cosine t dt. So this is the integral from 0 to pi of 2 sine t minus 2t cosine t dt. Let me set up a second integral. What is the integral along C2? Dot dr. So f along R2 of t is 2y R2 of t is the y coordinate is 0. 9 minus t 0. So we're going exactly like that. So f of R2 of t is 2y, y is 0, minus 2x, minus 2 pi minus t, which is 0, 2t minus 2 pi. So I'm taking the dot product of 0, 2t minus 2 pi, with r prime of t is minus 1, 0. This is a 0. I'm going to go 0 with 0. Let's see, what is this integral? The integral of sine t is cosine t. Actually, we already saw what this is. This is the integral from 0 to pi of 2 sine t is 4. Minus 2 times the integral from 0 to pi to cosine t dt. So this is really just remembering techniques from first year calculus. Let me write down this integral again on the computer. So the left-hand side of Green's theorem is the integral from 0 to pi sorry, 2 sine t minus 2t cosine t dt. So this is 2 integrals. The integral from 0 to pi of 2 sine t dt is minus 2 cosine t evaluated from 0 to pi. That's minus 2 cosine pi minus cosine 0. This is minus 1 minus 1. Minus 2 times minus 2 is 4. And what is the integral from 0 to pi of 2t cosine t dt. This is integration by parts. You have 2t, the derivative is 2. You have cosine t, the derivative, the integral is sine t. So this is 2t sine t evaluated from 0 to pi minus the integral from 0 to pi of 2 sine t. Okay. This is 0. This is minus 4. And we get minus 4. So this minus this is 4 minus minus 4, which is 8. So everything is okay, except I'm off by a minus sign. This is supposed to be exactly what we got when we computed the right-hand side. So why is my off by a sign? So I'm computing around this curve. Okay. I'm off by a minus sign because I drew the curve like this, going around this way and back this way. But you have to draw your curves counterclockwise. The Green's theorem, because the direction makes a difference. I have to go this way. It just reduces everything, changes the sign. So I do get a minus 8. So everything is correct once I just change the orientation of the curve. I have to go around the curve counterclockwise. So if I'm walking around the curve, the outside is to my right and the inside is to my left. So with that change, everything works out perfectly. Okay, so there's several takeaways from this. One is you have to be careful. 2 is there is a lot of work involved here. So this is generally you expect in a mathematics class, if you go through the semester, the material gets more and more sophisticated, more involved, because it uses everything you've done before. And for us, as we go through vector calculus, we end with Green's theorem. So you should expect this is the most technically difficult part of the class. But if you can manage to understand what's going on and do some problems, then you really learn quite a lot of mathematics. That's actually a very good thing. Okay. All right, so that's it for today. There's a little more on Green's theorem I'll talk about next Monday. But I'll also, and next Wednesday is just review for the final exam. Final exam is comprehensive, that is, it covers the whole course, which is a good thing, because if we just cover what we did since the second exam, it's the hardest material, and you're going to have some easier questions on the exam. And a good review for the course is what? Well, the review for exam 1, the review for exam 2, and I'm going to put out sending, in addition to the homework, some review problems from chapter 17. So you get some idea of the level of difficulty of the final exam. And I'm obviously not going to give you a problem like this on the final exam, because it can take an hour to do the problem, and you only have 2 hours for the exam. So that's the story. Any questions before we end? Looks like it's going to be a beautiful day. I hope everyone gets a chance to enjoy it. And then have an office hour, it's not an office hour, but a problem session at 7 o'clock tonight if you have questions. Encourage you to log in. And if you have questions that come up before Monday and you want to ask me, send me an email and I can arrange a time later in the week or over the weekend. I'll be able to answer you. Okay. That's it then. How much do you need to pass the final exam? Well, normally passing is a 60 on the exam. So let's say 60%. So that's what you need to pass. If the exam is 100 points, you need a 60. If the exam is 200 points, you need 120. Okay, be well. See you Monday.